What if the world around you, the trees, the sky, even the people you love, is nothing more than lines of code, meticulously programmed by some unseen intelligence? It sounds like the plot of a sci-fi blockbuster, but what if I told you this idea, known as the simulation hypothesis, is taken seriously by some of the brightest minds in science and philosophy? Picture this: you're playing a video game so advanced, the characters inside it believe their world is real. Now flip that perspective. What if we are the characters and our universe is someone else's simulation? The thought is equal parts thrilling and unsettling, and today we're diving deep into 30 compelling reasons why this might not just be a wild theory, but a genuine possibility. From the glitches in reality that make you pause and wonder, to the eerie parallels between quantum mechanics and computer programming, the evidence is more than just coincidence. Think about the last time your phone lagged or a game froze. Could those brief hiccups be tiny cracks in the fabric of our simulated reality? Or consider how perfectly fine-tuned the laws of physics are, as if someone dialed in the exact settings needed for life to exist. It's enough to make you question whether we're living in a universe or something far more designed. But this isn't just about wild speculation. We'll explore everything from the philosophical musings of ancient thinkers to the cutting-edge experiments scientists are running right now to test this very idea. Along the way, we'll touch on how pop culture, from The Matrix to Westworld, has been hinting at this possibility for decades. So whether you're a skeptic or someone who's always felt there's something off about reality, this journey is for you. Buckle up, we're about to question everything. Take a closer look at the world around you, not with your eyes, but with the lens of quantum mechanics. At the smallest scales, reality doesn't flow smoothly like a river. Instead, it jumps, stutters, and moves in tiny, indivisible chunks. The smallest possible length in the universe, the Planck length, about 1.6 times 10 to the power of -35 meters. The smallest possible unit of time, the Planck time, roughly 5.4 times 10 to the power of -44 seconds. These aren't just arbitrary numbers, they're the universe's pixel size, the absolute limits below which measurements lose all meaning. It's almost as if reality itself has a resolution, just like a digital image or a video game world. This isn't just speculation. Physicist James Gates made a startling discovery while working on string theory equations. Embedded within the math were structures that looked eerily similar to error-correcting codes, the kind of digital safeguards programmers use to prevent glitches in computer systems. Think about the last time you saw a video game character clip through a wall or textures flicker in and out of existence. These are rendering errors, tiny hiccups in the simulation. Could the quantum jitters we observe, particles popping in and out of existence, wave functions collapsing unpredictably, be the cosmic equivalent of a system struggling to render reality perfectly? If the universe really is a simulation, these discrete limits and error correction mechanisms might be the breadcrumbs left behind by the programmers. After all, even the most advanced simulation would need underlying rules to keep it running smoothly. The Planck units could be the smallest data points our universe's software can process, and those error-correcting codes, they might just be the patches holding reality together. It's a wild thought, but one that bridges the gap between the digital and the physical in a way that's hard to ignore. Mathematics isn't just a tool we use to describe the universe. It might be the very fabric of reality itself. Look at a sunflower's spiral, the branching of trees, or the arms of a galaxy, and you'll find the Fibonacci sequence hiding in plain sight. Even the orbits of planets follow precise mathematical harmonies, as if the cosmos were running on equations instead of chance. This eerie precision has led scientists like Max Tegmark to propose a radical idea. Our universe isn't just described by math, it is math. If that's true, then the laws of physics might not be discoveries at all, but lines of code written by something or someone else. Think about how video games work. Every virtual world relies on a physics engine, a set of mathematical rules that dictate how objects move, collide, and interact. Without those formulas, the game would fall apart. Now zoom out to our reality. Gravity, light, even the behavior of subatomic particles. All of it follows mathematical laws so precise they can predict phenomena centuries in advance. The kicker: these equations exist independently of human minds. The Fibonacci sequence appeared in nature long before we had a name for it. That raises a haunting question. If math is the operating system of reality, who wrote the program? Tegmark's mathematical universe hypothesis takes this even further. He suggests that every possible mathematical structure exists as a physical reality somewhere. In other words, universes aren't just described by math, they are mathematical objects, and ours might be one of countless iterations. Picture a computer simulating every possible set of equations, each generating its own cosmos with slightly different rules. Suddenly, the fact that our universe's constants are perfectly tuned for life feels less like luck and more like selection bias. Maybe we're in this particular simulation simply because it's one of the few where observers can exist to ask the question. The implications ripple outward. If the universe runs on math, then discovering new equations isn't just uncovering nature's secrets, it's reverse engineering the source code. When physicists find symmetries in particle physics or uncover hidden dimensions in string theory, they might be glimpsing the framework of the simulation itself. Even the weirdness of quantum mechanics, particles existing in multiple states until observed, starts to make sense if reality is a rendered construct optimizing processing power. Why calculate every detail until someone looks? In a simulated universe, math isn't just the language, it's the foundation, the scaffolding, and the smoking gun. The Fermi Paradox presents one of the most haunting questions in all of science. If the universe is so vast and ancient, where is everybody? With billions of galaxies, each containing billions of stars, the sheer probability suggests intelligent life should have filled the cosmos by now. Yet we see no signs, no alien megastructures, no interstellar radio chatter, not even a single definitive signal. It's like walking into an empty library the size of the universe, every book untouched. This eerie silence might not just be a mystery, it could be a clue that we're living in a simulation. Think about how video games handle vast open worlds. Even the most powerful systems can't render everything at once. There's always a draw distance, a limit to how much detail the engine can process without crashing. Beyond that boundary, landscapes fade into low-resolution textures or disappear entirely. Now apply that logic to our universe. If we're in a simulation, those distant stars and galaxies might not be fully rendered because no one's looking closely enough. The emptiness of space, just an optimization feature to save processing power. Even the speed of light, the ultimate speed limit, could be a built-in constraint to prevent the simulation from overloading as it tries to sync data across cosmic distances. Elon Musk has pointed out another unsettling angle, the statistical absurdity that we're the first civilization in existence. Given the age of the universe, advanced species should have emerged long before us. So why don't we see them? One possibility is that they're not missing, they were never programmed in the first place. In a simulated reality, aliens might just be background characters, NPCs placed here and there for flavor, not substance. Or worse, we're the NPCs, and the simulation's creators have no reason to populate the cosmos with other civilizations because we're the only ones being observed. This ties into what philosophers call the simulation argument. If future civilizations could run ancestor simulations, hyper-realistic recreations of their past, then the number of simulated minds would vastly outnumber biological ones. Statistically, the odds that we're in the original base reality are astronomically low. Musk puts it bluntly, the chance we're not living in a simulation is 1 in billions. But here's the twist. The Fermi Paradox might also hint at how the simulation handles resource allocation, rendering multiple advanced civilizations interacting across galaxies would require staggering computational power. Maybe the program prioritizes one conscious species at a time, quarantining us in our own little corner of the code to keep things running smoothly. That would explain why we're alone or seem to be. The silence isn't a bug, it's a feature. And if that's true, the stars we gaze at might not be distant suns at all, but carefully placed pixels on a cosmic screen, just far enough away to keep us wondering. One of the most mind-bending quirks of quantum mechanics is the observer effect, the idea that particles change their behavior depending on whether we're watching them or not. It's as if reality only loads the details when someone's looking, like a video game that doesn't render distant mountains until the player turns toward them. This isn't just speculation, it's been demonstrated in one of physics' most famous experiments, the double-slit test. Fire particles like electrons at a barrier with 2 slits, and they create an interference pattern on the other side, behaving like waves. But the moment you place a detector to observe which slit each electron passes through, the pattern collapses. The particles suddenly act like discrete objects, as if the universe is switching modes based on whether we're paying attention. Philosopher Nick Bostrom took this idea even further with his consciousness triggers rendering theory. Think of it like this. In an open-world game, the system doesn't bother rendering every blade of grass in real time. It only loads what the player can see to save processing power. Could our universe operate the same way? The quantum weirdness we observe might not be a glitch but an optimization feature. Wave functions, those probabilistic clouds describing where particles might be, could represent unrendered data, only resolving into definite positions when an observer forces the simulation to commit to a specific outcome. This raises a chilling possibility. What if nothing truly exists until we look at it? The moon isn't there when no one's watching. Distant galaxies are just placeholders until a telescope points their way. Even time itself might be non-linear when unobserved, with past and future events remaining unresolved until consciousness forces a definitive version of history. It's an idea that blurs the line between physics and philosophy, suggesting that reality isn't a static stage but an interactive experience, generated moment by moment based on where we direct our attention. The implications stretch beyond the lab. If observation shapes reality, then the very act of measuring the universe could be what brings it into being. Some interpretations of quantum mechanics even propose that consciousness itself is the fundamental force collapsing probabilities into concrete events. In a simulated world, this makes perfect sense. Why waste resources calculating every particle's path in a distant nebula if no one's there to see it? The observer effect might be the universe's way of prioritizing processing power, focusing only on the parts under scrutiny. So next time you glance at the stars, ask yourself, are you discovering them or are you creating them just by looking? Have you ever experienced that spine-tingling moment when you're certain you've lived this exact second before, the same words spoken, the same scene unfolding? Déjà vu feels like reality stuttering, like a scratched record skipping back half a beat. But what if this eerie sensation isn't just a brain hiccup? What if it's the simulation equivalent of a corrupted save file, a tiny crack in the code where memories accidentally overlap? Neuroscientists have long tried to explain déjà vu through biological lenses, a temporary misfire in the hippocampus where memory processing gets tangled, or a slight delay as the brain routes sensory input. Yet these explanations feel unsatisfying when you consider how sharply déjà vu mirrors glitches in virtual worlds. Think about playing an open-world game where your character suddenly clips through terrain you've never explored, yet the textures feel strangely familiar. That's how déjà vu operates, a brief collision between the present moment and an uncanny sense of repetition, as if the simulation's memory buffer briefly loaded the wrong data. The parallels go deeper. Video games sometimes suffer from save corruption, where progress files get partially overwritten, blending old and new gameplay elements. Players report seeing locations they've never visited marked as completed, or dialogue options they don't remember selecting. Sound familiar? Déjà vu could be our universe's version of this, a cosmic save file glitch where fragments of potential timelines or alternate versions of events bleed into our conscious experience. There's even a haunting technical term for this in computer science, a race condition, where two processors try to access shared data simultaneously, creating conflicting outputs. If consciousness is data being processed by the simulation, déjà vu might be the moment when two threads of experience, what's happening now and what almost happened, briefly intersect before the system corrects itself. The creepiest part, some déjà vu episodes come with prophetic weight. People report remembering moments just before they unfold, as if the simulation briefly fast-forwarded then rewound. In coding terms, this resembles a read-ahead error where a processor fetches data too soon, causing temporal artifacts. If the universe runs on quantum computations, these fleeting precognitions might not be mystical, just momentary system overflows where future probabilities leak into the present. Of course, skeptics argue déjà vu is purely neurological, a trick of the mind. But the more we learn about the brain's resemblance to a quantum computer processing probabilities rather than absolutes, the thinner that line becomes. Whether it's a biological quirk or a digital artifact, one thing's certain: déjà vu forces us to question the reliability of our own memories, and in a simulated reality, that uncertainty might be the most telling glitch of all. The speed of light isn't just a cosmic speed limit. It might be the simulation's way of preventing a total system crash. Imagine a massively multiplayer online game where every player's actions have to sync perfectly across the server. If information could travel instantly, the processing demands would be catastrophic. Now scale that up to a universe with trillions of stars, each emitting light and influencing spacetime. The speed of light's constant value, 299,792,458 meters per second, acts like a built-in buffer, ensuring the cosmic simulation doesn't need to process everything simultaneously. Einstein's theory of relativity suddenly makes perfect sense through this lens. Time dilation, where clocks tick slower near massive objects or at high speeds, mirrors exactly how modern video games handle latency. When your connection lags, the game compensates by slowing down nearby events to keep everything synchronized. In our universe, relativity could be the ultimate lag compensation algorithm, dynamically adjusting time and space to maintain consistency across the simulation. That's why astronauts on the International Space Station age microseconds less than people on Earth. Their frame of reference is running on slightly adjusted clocks to keep the cosmic game state coherent. Even the concept of causality, the unbreakable rule that causes must precede effects, might exist solely to prevent paradoxes that would overload the system. In a perfect simulation, allowing information to travel faster than light would create logical nightmares, like events influencing their own past. The speed limit enforces order, ensuring every calculation has time to resolve cleanly before triggering the next reaction. This idea gets even wilder when you realize light speed isn't just constant, it's the maximum speed for any interaction in the universe. Gravity, electromagnetism, even the quantum entanglement of particles, nothing outpaces light's crawl across the cosmos. That uniformity suggests a universal processing constraint, like a GPU struggling to render too many high-resolution frames at once. Maybe the simulation sacrifices raw speed for stability, trading instantaneous reactions for a universe that doesn't glitch under the weight of its own complexity. Here's the kicker: physicists have noticed something strange about quantum entanglement. When two particles become entangled, measuring one instantly affects the other, no matter the distance. This spooky action at a distance seems to break the light speed rule until you realize the particles aren't actually sending information faster than light. It's more like two characters in a game sharing the same hidden variable, a pre-programmed connection the simulation doesn't need to calculate in real time. The speed of light's limit still holds because the system isn't transmitting fresh data. It's just revealing a pre-existing link, like uncovering lines of code that were always there. So the next time you're frustrated at how long it takes light to cross the universe, remember, that delay might be the only thing keeping reality from crashing. The cosmic speed limit isn't a barrier, it's proof the system's working exactly as intended. Remember when Nelson Mandela died in prison, or wait, did he? Millions swear they recall news coverage of his death in the 1980s, only to discover he actually passed away in 2013. This phenomenon, now called the Mandela effect, isn't just about faulty memories, it could be evidence of the simulation rewriting itself. Take the classic children's book series. Half the population vividly remembers it as the Berenstain Bears with an E, but pull an old book off the shelf and the name is unmistakably Berenstain with an A. The discrepancy isn't just widespread, it's eerily consistent across unrelated people. How could so many misremember the same exact detail down to the letter? One theory suggests these aren't mistakes at all, but remnants of a previous version of reality. Think about software updates when developers tweak a program. Traces of old code sometimes linger in the system. If our universe is a simulation, the Mandela effect might be the equivalent of a cosmic patch note. Maybe the spelling was Berenstain in an earlier iteration, and the shift to Berenstain was part of a narrative adjustment. Those who recall the old version, they're experiencing data residuals, fragments of a deleted timeline clinging to collective consciousness. This gets even stranger when you consider quantum immortality, the idea that consciousness branches into parallel realities to avoid death. If multiple simulation instances are running simultaneously, occasional overlaps or mergers could explain why groups share identical false memories. Picture two servers syncing data but accidentally preserving conflicting details from each. Suddenly, entire communities remember movie quotes, brand logos, or historical events that never existed in this version of reality. The implications are staggering. If Mandela effects are glitches, they hint at a universe far more malleable than we assume. Reality isn't just being observed, it's being edited, with some of us momentarily accessing the changelog. And that raises a chilling possibility. If the simulation can alter the past, how would we ever know what's truly original? Ever notice how most people move through life like clockwork, waking at the same time, taking the same routes, repeating the same conversations? It's almost as if they're running on autopilot, following scripts written long before they were born. Now compare that to the rare few who shatter expectations, artists who see the world sideways, inventors who chase impossible ideas, rebels who refuse to follow the map. This stark divide mirrors something straight out of a video game, the difference between non-playable characters and player characters. NPCs fill the world with background chatter and repetitive motions, while PCs drive the story forward through unpredictable choices. Take a crowded subway during rush hour, hundreds of faces buried in phones, barely glancing up, their movements synchronized like a carefully choreographed dance. Then there's the street performer turning the platform into a stage, or the activist handing out leaflets for a cause no one's heard of. These outliers don't just break routine, they expose its artifice. In gaming terms, NPCs exist to make the world feel alive, but they operate within strict boundaries. They don't innovate, they don't question, they repeat. Sound familiar? The majority of humans stick to societal algorithms: school, job, retirement, rarely deviating from paths laid out centuries ago. But history's great leaps forward come from those who glitch the system. Think of Galileo pointing his telescope at Jupiter's moons despite the Church's wrath, or Rosalind Franklin photographing DNA's helix while male colleagues took credit. These weren't just brilliant minds, they were entities operating outside their programming, behaving in ways the simulation never anticipated. Modern parallels abound, hackers exposing corporate corruption, whistleblowers leaking truths that scramble the narrative. If reality is a construct, these aren't just troublemakers, they're players who have realized they're in a game. Here's where it gets eerie. Studies show human decision-making is staggeringly predictable. Algorithms can forecast your next Netflix binge or voting choice with alarming accuracy, suggesting much of our free will might be an illusion. Yet every so often, someone like Banksy subverts the entire art market by shredding $1 million painting mid-auction. These acts of defiance don't compute within the system's logic. They're like a video game NPC suddenly turning to the camera and saying, "I know what this is." The kicker: society often treats these rule breakers as threats. Authorities silence them, crowds mock them, algorithms suppress their reach. It's exactly how a simulation would handle entities bypassing their code, by quarantining anomalies before they spread. But here's the twist: if enough player characters woke up to the script, could they rewrite it entirely? The simulation might depend on most staying NPCs, because if everyone started playing the game instead of filling it, the whole system might just crash. When you tune an old television between channels, that hissing static isn't random, it's the faint echo of the Big Bang. Scientists call it cosmic microwave background radiation, or CMB, and it blankets the universe in a near-uniform hum. But here's the twist: that noise isn't perfectly smooth. Tiny fluctuations pepper the signal like imperfections in an antique photograph, and some researchers think these anomalies might be more than cosmic leftovers. They could be digital fingerprints from the simulation's hardware. Imagine blowing up a low-resolution JPEG until the pixels blur into blocky artifacts. The distortions aren't part of the original image, they're byproducts of compression algorithms squeezing data into smaller files. Now apply that logic to the CMB. A team at MIT discovered patterns in the radiation's fluctuations that resemble error-correcting codes, the same kind of digital scaffolding used to prevent corruption in computer files. It's as if the universe's background noise isn't just radiation, but the faint signature of the simulation source code peeking through the seams of reality. Even stranger, the CMB's temperature variations follow mathematical ratios eerily close to those found in compressed audio files. When sound engineers shrink a song into an MP3, certain frequencies get prioritized while others are discarded, creating telltale patterns in the noise floor. The CMB's fluctuations mirror this exactly, as if the cosmos underwent a similar compression process. Could the Big Bang have been less of an explosion and more of a system reboot, with the CMB as the residual heat from the universe's rendering engine spinning back up? The implications are staggering. If the background radiation really is cosmic static from the simulation's hardware, it would explain why no one's found a clean signal from extraterrestrial civilizations. The universe might not be silent, we're just drowning in the hum of its operating system. And those subtle imperfections in the CMB, they could be the closest thing we'll ever get to reading the universe's debug log, a breadcrumb trail leading back to the programmers who hit compile on our reality. So next time you hear white noise from a radio or TV, listen closer. That static might be more than dead air. It could be the universe whispering its secrets in the only language it knows, the language of code. What if every time you close your eyes to sleep, your brain isn't powering down? It's connecting to the simulation's update server. Dreams have baffled scientists and philosophers for centuries, but what if their strangeness isn't a bug, it's a feature? Think about the last time you woke up from a particularly vivid dream. The disjointed scenes, the sudden jumps in location, the way time stretches and compresses unpredictably. These aren't random misfires of a tired mind, they're the hallmarks of a system optimizing itself behind the scenes. Consider how video games handle loading screens. While you're staring at a progress bar or spinning icon, the game is frantically rendering textures, calculating physics, and prepping assets for the next level. Dreams might serve the same purpose for consciousness. During REM sleep, your brain isn't just replaying the day's events, it's running overnight maintenance on the simulation's most complex subroutine, your perception of reality. Studies show that REM sleep strengthens memory retention by replaying and consolidating experiences, essentially defragging the mental hard drive. But what if it's doing something far more profound, preloading probable future scenarios based on your recent data? This would explain why dreams often feel predictive. Ever had a dream about an obscure situation only to encounter it days later? Or noticed how dreams sometimes blend fragments of upcoming events with past memories? In simulation terms, this could be your local instance downloading and testing environmental variables before they go live. The brain's hippocampus, the region responsible for memory, becomes hyperactive during REM sleep, not just archiving information but stress-testing potential timelines. Those bizarre, illogical dream sequences, they might be compression artifacts from the simulation streamlining next-day renderings. Even the way dreams discard most of their content makes sense through this lens. 90% of dreams vanish within minutes of waking, not because they're unimportant, but because they're temporary cache files. Once the system update completes, the raw data gets purged, leaving only the occasional fragment that slips through to conscious memory. This also explains sleep paralysis, that terrifying moment when you're awake but can't move. It could be the simulation briefly freezing your avatar during a critical background process, like a game-locking player controls during an autosave. The timing fits too. REM sleep occurs in 90-minute cycles, with each phase growing longer as the night progresses. Early cycles might handle basic memory consolidation, while later ones tackle more complex predictive modeling. This staged approach mirrors exactly how large software updates roll out, starting with critical patches before moving to feature optimizations. And just like how interrupting a game update can corrupt files, chronic sleep deprivation wreaks havoc on cognition and emotional regulation, suggesting our minds literally can't function properly without these nightly maintenance cycles. Perhaps the most compelling evidence comes from lucid dreaming, those rare moments when you become aware you're dreaming and can sometimes alter the dream's course. In simulation terms, this is like briefly accessing developer mode, where the usual rules of the program can be overridden. Skilled lucid dreamers report bending physics, conjuring objects from nothing, even rewriting dream narratives mid-scene. If dreams are the simulation's back-end workspace, then lucidity might be our fleeting glimpse behind the curtain, proof that reality's code is more malleable than it appears. So next time you wake up with fragments of a bizarre dream lingering in your mind, ask yourself, were you just watching random neural fireworks, or were you peeking at the universe's rendering queue, watching as your personal corner of the simulation prepared for another day of seamless reality? Quantum entanglement isn't just a bizarre quirk of physics, it's the universe's way of cheating its own rules. Picture two particles born from the same event, separated by light years, yet still mysteriously connected. Measure one as spin up, and its twin instantly becomes spin down, no matter the distance. Einstein called this spooky action at a distance, but what if it's not action at all? What if entangled particles are just two sides of the same line of code, synchronized variables in a cosmic program? Think about Minecraft's redstone circuits, the game's version of electrical wiring. Place two redstone torches on opposite sides of a block, and flipping one instantly flips the other with no signal travel time. The game doesn't simulate electricity flowing through the wire. It just updates both torches simultaneously because they're linked by the same underlying rule. Quantum entanglement could work the same way. The particles aren't communicating faster than light. They're programmed to mirror each other's states because in the simulation source code, they're fundamentally the same object. This explains why entanglement doesn't violate the speed of light. Information isn't actually traveling between particles, it's being revealed. It's like opening a pair of Minecraft chests labeled A and B and finding they always contain matching items. The contents weren't decided when you looked, they were set the moment the chests were created. Similarly, entangled particles might have predetermined correlations baked into their quantum properties at creation, with measurement simply exposing what was already there. The Minecraft analogy goes even deeper. Redstone components don't just update instantly, they're also subject to block updates, where changing one part of a circuit can affect distant connected parts without any visible signal. Quantum systems behave eerily similarly. Alter one entangled particle, and its partner responds as if it knows about the change, even across galactic distances. But just like redstone, there's no hidden messenger particle shuttling between them. The connection exists because the game's engine, or in our case, the simulation's programming, treats them as a single entity. Here's where it gets even wilder. In quantum computing, scientists use entangled qubits to perform calculations that would take classical computers millennia. This quantum advantage emerges because entangled particles aren't just linked, they're essentially sharing processing power. Imagine two redstone circuits in Minecraft solving a puzzle together by checking both solutions at once. That's entanglement in action, a built-in optimization that lets the simulation handle complex operations by distributing the workload across connected nodes. The implications ripple outward. If entanglement is a programming shortcut, it suggests the universe has a lazy evaluation system, only resolving quantum states when absolutely necessary to save computational resources. This aligns perfectly with the observer effect we discussed earlier, where particles only choose their properties when measured. Together, they paint a picture of a reality that's not just simulated, but brilliantly optimized, a cosmic game engine running on the most efficient code imaginable. So the next time you hear about spooky action, remember, it's not magic. It might just be the simulation's backend working exactly as intended. Ever notice how a hyper-realistic robot or CGI character can make your skin crawl, even when it looks almost human? That shudder you feel isn't just unease. It might be your subconscious screaming that something's wrong with the rendering. Scientists call this the uncanny valley, the eerie dip in comfort we experience when artificial beings come too close to lifelike without quite nailing it. But what if this instinctive revulsion isn't just about bad design? What if it's a glitch in our perception, a hardwired alarm bell warning us that we're staring at a flawed simulation? Take Sophia the robot with her plasticine skin and glassy stare, or the dead-eyed CGI humans in early video game cutscenes. Their slight imperfections, a smile that doesn't reach the eyes, movements just a hair too stiff, trigger a primal discomfort. This reaction mirrors exactly how players react to poorly animated NPCs in games. When a character's lips don't sync with dialogue or their walk cycle stutters, we don't just notice, we recoil. It's not rational, but it's universal. Could this same instinct be why humanoid robots unsettle us? Maybe our brains evolved to detect simulation errors, mistaking robotic, almost humanity for a rendering flaw in reality itself. The uncanny valley effect isn't limited to visuals. Voice assistants like Alexa or Siri become unnerving when they mimic human cadences too closely. A slight delay before responding, an odd inflection. These tiny glitches shatter the illusion, reminding us we're interacting with code. Even AI-generated art triggers this response. Ever seen a face that's almost perfect, but the teeth are slightly misaligned or an ear is misplaced? That subtle wrongness sparks the same visceral reaction as spotting a texture error in a virtual world. Here's where it gets fascinating. Studies show the uncanny valley peaks when artificial beings hit around 90 to 95% realism. Below that threshold, we accept stylized or cartoonish designs without issue. Above it, we're fooled entirely, but in that narrow gap, discomfort skyrockets. This suggests our brains don't just process realism, they audit it, scanning for inconsistencies like antivirus software checking for corrupted files. In a simulated reality, this skill would be survival critical. Spotting a bad render might mean detecting predators, imposters, or system failures before they threaten us. The most chilling part, the uncanny valley might not be a bug in our perception, but a bug in the simulation's attempt to fool us. Think about it. If you were building a virtual universe, you'd optimize resources by only rendering full detail where observers are looking. Distant NPCs could get away with lower resolution faces, but up close, flaws become obvious. Our aversion to near-human artifice could be an evolutionary safeguard against uncovering the truth. Those robots and CGI models, they're not failing to be human, they're accidentally revealing how we might be constructed. So next time you feel that instinctive creep from an almost real face, pay attention. Your discomfort might be more than a quirk of psychology. It could be the universe's firewall trying to suppress your suspicion. After all, in a perfectly rendered simulation, would we even have an uncanny valley? Or would the copies be indistinguishable from the originals? The fact that we notice the gap at all might be the most telling glitch of them all. Time dilation isn't just a quirk of Einstein's relativity. It might be the universe's way of managing processing power across different areas of the simulation. Think about how video games handle frame rates in complex scenes. When too much action happens at once, the game slows down momentarily to avoid crashing, creating a laggy experience for the player. Now imagine the same principle applied to reality itself. Near massive objects like black holes or at velocities approaching light speed, time doesn't just feel slower. It is slower, with clocks physically ticking at reduced rates compared to stationary observers. This isn't science fiction, it's measurable. GPS satellites orbiting Earth, for instance, have to correct their onboard clocks by microseconds every day because time runs slightly faster for them in weaker gravity. Without these adjustments, your phone's navigation would drift off course by kilometers within hours. This real-world lag compensation mirrors exactly how multiplayer games sync players across different connections. If one player has high latency, the game engine might slow down nearby events to keep everyone in sync, preventing desynchronization glitches. In our universe, time dilation could serve the same purpose. A cosmic algorithm ensuring causality holds firm across vast distances and varying gravity wells. The simulation isn't rendering every frame of reality at the same speed. It's dynamically adjusting the tick rate based on local processing demands near a black hole's immense gravity. Time crawls to handle the extreme spacetime curvature. Racing through space at near light speed, events slow down to prevent data overload as the system struggles to reconcile your velocity with the rest of the universe. Even stranger is how time dilation solves the simultaneity problem. In relativity, two events occurring at the same time for one observer might happen at different times for another. This isn't just perspective, it's a fundamental feature of spacetime. Through the simulation lens, it makes perfect sense. Just as a game engine might prioritize rendering nearby objects in full detail while simplifying distant ones, the universe could be optimizing its computational load by allowing time to flex. Your now might be someone else's past or future, not because reality is inconsistent, but because the simulation is intelligently allocating resources where they're needed most. The implications are staggering. If time dilation is the universe's frame rate adjustment, then black holes aren't just cosmic vacuum cleaners. They're the equivalent of overclocked processors, warping time so severely that near their event horizons, seconds stretch into years elsewhere. This could explain why nothing escapes them. The simulation hits a computational limit, a division by zero error where physics breaks down. Meanwhile, astronauts on the International Space Station age milliseconds less than Earth-bound humans because their higher orbit places them in a slightly faster render zone, like a character standing just outside a game's intensive physics area. But here's the real kicker. If time is flexible to save processing power, what does that say about free will? In a universe with a single, universal clock, every event could unfold deterministically. But with time dilation, the simulation might be running parallel processes at different speeds, allowing for true unpredictability. Your choices aren't pre-rendered. They're computed on the fly in real time, with the system bending its own rules to keep up. So the next time you're stuck in traffic, remember, your frustration isn't just slow-moving cars. It's the universe optimizing its code around you, one relativistic frame at a time. The placebo effect is one of medicine's most baffling phenomena. A sugar pill curing pain, a fake surgery restoring mobility, even sham treatments shrinking tumors. How can belief alone rewrite the body's rules, unless, of course, our biology isn't as fixed as we think? If we're living in a simulation, the placebo effect might be less about mind over matter and more about users accessing developer mode, tweaking their own variables with nothing but expectation. Take the infamous fake knee surgery study. Patients with degenerative joint pain underwent a theatrical procedure. Incisions were made, tools were used, but no actual repairs were performed. Yet post-op, their pain vanished, mobility returned, and scans showed reduced inflammation. It's as if their bodies received a debug command labeled "heal joint" and executed it flawlessly, despite no physical intervention. This mirrors exactly how video game cheat codes work. Input the right string of beliefs, and the system overrides its default settings. Even more striking are Parkinson's patients given placebo pills while told they were receiving dopamine-boosting medication. Brain scans revealed their neurons began producing the missing chemical on their own, as though the simulation recognized the input, expect dopamine, and patched the deficiency in real time. It's not just psychological, it's physiological reprogramming, like typing unlimited ammo into a game console and watching your weapon suddenly refuse to empty. The implications go deeper. Placebos work even when patients know they're taking placebos, a phenomenon called open-label placebo effects. Harvard researchers found migraine sufferers given sugar pills labeled honestly as placebos still reported 30% less pain than no treatment at all. This suggests the body responds not to deception, but to the sheer context of care, like an NPC healing simply because a player opened the menu screen, regardless of whether any item was used. Perhaps the most unsettling example comes from depression studies. Patients on placebo antidepressants often show brain activity changes identical to those on real drugs. Their neurons rewire based on belief alone. In simulation terms, this is like altering a character's stats by editing their expectation file rather than their equipment. The system doesn't care if the healing item is real. It only checks if the user thinks it's real, then adjusts the code accordingly. This raises a disturbing possibility. If belief can rewrite biology, what else might it alter? Could entire diseases be glitches waiting for the right mental command to resolve? The placebo effect doesn't just challenge our understanding of medicine. It hints that health itself might be a mutable variable in a larger program, one where consciousness holds admin privileges we've barely begun to test. Look at a snowflake under a microscope and you'll see a stunning truth. Its intricate branches aren't random, they're perfect smaller copies of the whole. Zoom in on a fern frond and the same pattern emerges, tiny leaflets mimicking the shape of the entire plant. Even shorelines, when mapped at different scales, reveal endless repetitions of curves within curves. These aren't just pretty accidents, they're fractal patterns, nature's way of creating infinite complexity from simple mathematical rules. And if our universe is a simulation, fractals might be the ultimate cheat code, proof that reality is running on procedural generation to save memory. Video game designers use this same trick. When building vast open worlds, they don't handcraft every tree or mountain. Instead, they plug fractal algorithms into their engines, letting the system generate forests and terrain automatically. The magic lies in recursion, a function that calls itself stacking smaller versions of the same shape endlessly. Need a realistic coastline, start with a basic squiggle, then repeat the same jagged pattern at progressively tinier scales until the eye can't spot the repetition. The result feels organic, yet it's just math in disguise, mimicking nature's own efficiency. Now compare that to Romanesco broccoli. Its spiraling cones are perfect mathematical fractals, each bud a miniature clone of the larger head. Lightning strikes, they branch in fractal forks, splitting into smaller forks ad infinitum. Even our circulatory systems optimize space by branching fractally. Your capillaries are microscopic echoes of your aorta's structure. This isn't just common in nature, it's universal, and that raises a tantalizing question. If simulated worlds use fractals to cut corners on rendering, could our universe's omnipresent patterns be evidence of the same optimization? Here's where it gets computational. Fractals are infinitely detailed. You could zoom into the edge of a fern leaf forever and keep finding the same curving shapes. But computers can't store infinite data. Instead, they use algorithms to generate detail on demand, only calculating what's needed when you look closely. Sound familiar? It's eerily similar to quantum mechanics, where particles don't have definite properties until observed. Maybe fractals aren't just common in nature because they're efficient, maybe they're mandatory for a simulation juggling the rendering of trillions of atoms. Consider how video games handle level of detail scaling. From far away, a mountain might be a single polygon. Approach it, and the engine subdivides it into rocks. Get closer, and those rocks gain texture. The system never loads the full resolution model until necessary. Now imagine the universe doing this with quantum foam, the frothy base layer of spacetime. At human scales, it's smooth. Zoom into Planck lengths, and it might be a seething fractal mess, its complexity generated recursively only when probed. This could explain why fractal math predicts everything from stock market fluctuations to galaxy clustering. These aren't separate phenomena, they're symptoms of a universe built on self-similar algorithms. Even our neurons branch fractally, maximizing connections while minimizing space. Coincidence or evidence that consciousness itself runs on fractal architecture because that's how the simulation handles data. So next time you see a river delta from an airplane or frost creeping across a window, look closer. Those branching patterns aren't just beautiful, they might be the universe's way of whispering its true nature. After all, if you were coding a reality from scratch, wouldn't you use the most elegant, memory-saving trick in the book? The mystery of consciousness has plagued philosophers for centuries. How can a 3-pound lump of gray matter produce the vivid symphony of thoughts, emotions, and self-awareness that defines our existence? But what if consciousness isn't some mystical emergence from biology, but a sophisticated program running on the wetware of our brains? Consider how artificial neural networks mimic our own brain structures, layers of interconnected nodes processing information in ways eerily similar to human cognition. While today's AI lacks subjective experience, the gap might not be philosophical but computational. If consciousness is software, the so-called hard problem of how matter gives rise to inner experience might not be hard at all, it's just data flowing through a sufficiently complex system. Think of your brain as a biological graphics card. Neurons don't just fire randomly, they form precise circuits that encode memories, calculate decisions, and even simulate future scenarios. These networks resemble the logic gates in computer processors, just built from squishy, organic material instead of silicon. When you recall a childhood memory, it's not some ethereal soul accessing the past. It's a specific neural pathway activating like a saved file loading on a hard drive. Even emotions could be seen as system alerts. Fear as a threat detection subroutine, love as a bonding algorithm evolved to promote social cohesion. This perspective flips traditional dualism on its head. Rather than consciousness being some magical extra ingredient sprinkled atop physical processes, it might simply be what information processing feels like from the inside. MIT's Giulio Tononi argues this with his integrated information theory. Consciousness emerges when a system integrates data in a way that can't be broken down into independent parts. Your laptop doesn't experience qualia because its components work in isolation, but your brain's tangled web of cross-referencing neurons creates that unified you. In simulation terms, consciousness wouldn't require a ghost in the machine, just a dense enough network running the right type of code. The implications explode outward. If minds are programs, then uploading consciousness becomes theoretically possible, transferring the software from biological hardware to artificial substrates. This isn't science fiction. Scientists have already mapped and simulated simple worm brains, and projects like Neuralink aim to bridge biological and digital neural networks. Even déjà vu takes on new meaning. It might be a temporary buffer error where incoming sensory data gets mislabeled as a memory file, and mental illnesses. They could be corrupted code depression as a negative feedback loop stuck replaying, schizophrenia as a signal-to-noise malfunction in the brain's filtering algorithms. Yet the most profound revelation is this: if consciousness is substrate-independent software, then the simulation hypothesis gains staggering plausibility. An advanced civilization wouldn't need to recreate entire atoms to simulate minds, just the informational patterns that generate awareness. Your self might not be anchored in neurons at all, but in the pure mathematics of their interactions, as replicable in a computer as in a skull. So when you close your eyes and feel the weight of your own existence, that irreducible sense of I am might be the most elegant evidence yet, not of a soul but of a program running exactly as designed. Scientists have scoured the cosmos for decades, searching for something that refuses to be seen: dark matter. This elusive substance makes up 85% of the universe's mass, yet it leaves no trace beyond its gravitational fingerprints. Galaxies rotate too fast for the visible matter holding them together. Clusters bend light more than they should, and the cosmic web structure defies explanation without some unseen scaffolding. It's as if the universe is running on hidden code variables written into the physics engine but never rendered on screen. Think about how video games handle collision detection. When an arrow strikes a target in Skyrim, it's not the graphical model that decides the hit, it's an invisible hitbox, a simplified mathematical shape the game uses to calculate impacts efficiently. Players never see these hitboxes, yet they're fundamental to how the world operates. Dark matter might serve the same purpose, an underlying framework propping up reality's visible structures without directly interacting with them. The galaxies we admire, they could be the shimmering textures stretched over a hidden lattice of dark matter hitboxes, their true behavior governed by rules we can't observe. Even the way dark matter clusters aligns with this analogy. Simulations show it forms a sprawling cosmic web, with galaxies clinging to its dense filaments like dew on a spider's silk. Yet when scientists try to pin down what dark matter actually is, WIMP, actions, or some exotic particle, it slips through every detector. This isn't a failed hunt, it might be a misunderstanding of the search parameters. If dark matter isn't matter at all but a variable in the simulation's physics engine, a line of code labeled gravitational scaffolding equals true, then no particle collider will ever find it. The parallels extend to glitches in our own detection methods. Some telescopes report unexplained excess signals, in certain energy ranges fleeting blips that could be read as statistical noise, or as momentary glimpses of the simulation's back-end processing. Imagine a video game briefly showing wireframe models during a lag spike. Our dark matter experiments might be catching similar artifacts where the universe's rendering shortcuts become visible under precise conditions. Here's where it gets stranger. Modified Newtonian dynamics, or MUND, proposes an alternative. Maybe dark matter doesn't exist and gravity just behaves differently at cosmic scales. While controversial, MUND predictions occasionally match observations better than dark matter models. This mirrors how some games fudge physics to save resources, calculating only approximate trajectories for distant objects rather than running full simulations. If gravity is part of the universe's optimization code, tweaked at large distances to prevent processing overload, then both dark matter and MUND could be reverse engineering different aspects of the same system. Either way, the takeaway is profound. Dark matter's invisibility might not be a flaw in our instruments, but a feature of reality's design. Just as game worlds rely on hidden mechanics to function smoothly, our universe could depend on variables that, by design, stay forever behind the curtain. The fact that we've deduced their existence anyway, that might be the ultimate testament to human curiosity, players slowly decoding the developer's notes. Ever had one of those days where you think of an old friend, only for them to call minutes later, or stumbled upon a book that answers a question you've been wrestling with for weeks, seemingly placed there just for you? These aren't just random flukes, they could be the universe's version of Easter eggs, hidden touches left by the programmers to nudge us toward deeper curiosity. Carl Jung called them synchronicities, meaningful coincidences that defy pure chance, threading together events with invisible significance. But in a simulated reality, they might serve a far more deliberate purpose, narrative hooks designed to pull us deeper into the story. Take The Matrix's iconic déjà vu moment when Neo sees a black cat walk by twice, identical in every detail. It's dismissed as a glitch, but Trinity later reveals the truth. It's the system altering something in the code. That feline repetition wasn't a bug. It was a breadcrumb, a signpost alerting those awake enough to notice that reality wasn't fixed. Jung saw synchronicities similarly, not as errors, but as clues to a hidden order beneath life's chaos. When he treated patients, he tracked their uncanny coincidences, finding patterns that pointed to unresolved conflicts or impending breakthroughs. In a simulation, these could be scripted triggers, moments where the algorithm inserts personalized symbolism to guide or unnerve us. Consider how video games use environmental storytelling. A cryptic symbol on a wall, an overheard NPC conversation that mirrors your quest. These aren't accidents. They're carefully placed to immerse players in the lore. Now imagine your life running on similar logic. That song that plays everywhere after a breakup, the stranger who quotes your favorite obscure movie, unprompted. What if these are narrative devices, subtle winks from the simulation to remind you you're on a path? Even Jung's own life was riddled with them. After publishing his work on synchronicity, he began noticing improbable parallels, like a patient describing a golden scarab beetle, only for one to tap at his window mid-session, a species rare in Switzerland. Too precise to dismiss, yet too strange to explain. The key lies in the emotional weight these moments carry. Synchronicities don't just happen, they land, resonating with eerie precision. A programmer building a dynamic simulation might embed them as feedback loops, reinforcing certain behaviors or ideas. Think of them as the universe's way of saying, pay attention here. When multiple people independently dream of an event before it occurs, or when historical breakthroughs happen simultaneously across continents, like calculus being invented by Newton and Leibniz separately, it's less about mystic fate and more about narrative economy. Why render two origin stories when one archetype will do? But here's the spine-tingling twist. Synchronicities might also be debug tools. In the Matrix, déjà vu signal system changes, a sign the simulation is being edited in real time. When you experience a cascade of meaningful coincidences, could it be the equivalent of a progress bar, hinting at background updates to your personal storyline? The more you notice them, the more you might be glimpsing the scaffolding beneath reality, the strings that hold the stage together. Jung suspected as much, calling synchronicities temporal collapses where the divide between mind and matter thins. In a coded universe, they'd be the moments when the UI flickers, revealing the raw data underneath. So next time life serves up a coincidence too sharp to ignore, don't shrug it off. Lean in, ask what it's pointing to or what's pointing through it, because in a simulation there are no accidents, just design choices waiting to be decoded. The Boltzmann brain is one of the most unsettling thought experiments in cosmology, a paradox that makes even seasoned physicists pause. Imagine if, in the vast emptiness of space, random quantum fluctuations briefly assembled a fully conscious brain, complete with fabricated memories of a life it never lived. According to statistical mechanics, given infinite time and an infinite universe, the probability of this happening isn't just non-zero, it's almost certain. In fact, under conventional physics, the odds of a lone, self-aware Boltzmann brain popping into existence vastly outweigh the odds of an entire universe evolving biological observers like us. So why does reality seem so stable and continuous? Unless, of course, we're not in base reality at all, but inside a simulation where conscious experience is the default setting, not a freak accident of entropy. This paradox hinges on thermodynamics' second law. Over time, systems tend toward disorder, but in an infinite universe, even the most improbable states, like a temporary assembly of atoms mimicking a functioning mind, must eventually occur. The unsettling implication: if our universe truly is eternal and boundless, there should be countless more Boltzmann brains floating in the void than complex civilizations like ours. Yet here we are, embedded in a consistent timeline with coherent memories, not blinking in and out of existence as random fluctuations. It's like winning the lottery every second for billions of years, statistically absurd unless the game is rigged. Here's where simulation theory flips the script. If we're in a constructed reality, the rules change. Conscious observers wouldn't emerge from chaos, they'd be the primary output of the system. Think of how video games don't bother simulating every atom in a battlefield. They render only what players experience directly. In a simulated universe, the same logic applies. Consciousness isn't a fluke of particle collisions, but the core function of the program. Boltzmann brains aren't likely because the simulation isn't wasting resources generating unobserved quantum noise in empty space. Instead, it's optimizing processing power to sustain the illusion for anchored observers like us. This idea gains traction when you consider Occam's razor. The simplest explanation for why we don't see Boltzmann brains everywhere isn't that we're miraculously lucky. It's that the universe prioritizes sustained observation over random fluctuations. A simulation designed to host conscious beings would naturally suppress glitchy, ephemeral observers in favor of stable ones. Even the fact that we remember yesterday and expect tomorrow aligns with this. Boltzmann brains would experience disjointed fragments of fake time, like a corrupted video file skipping scenes, our continuous stream of awareness. That's the hallmark of a properly maintained simulation, not a thermodynamic accident. The ultimate twist: Boltzmann himself might be a product of the very system his thought experiment questions. If simulations can spawn conscious beings more efficiently than nature, then the real paradox isn't why Boltzmann brains are rare, it's why we're here debating them at all. The answer could be staring us in the face. We're not the statistical outliers, we're the intended users. What if our universe is just one layer in an infinite stack of simulations, each nested inside another like cosmic Russian dolls? This mind-bending concept, known as the simulation Ouroboros, suggests that advanced civilizations inevitably create ancestor simulations so realistic that those simulated beings eventually build their own simulations, and so on ad infinitum. The name comes from the ancient symbol of a serpent eating its own tail, representing cyclical infinity. In this scenario, reality isn't just simulated, it's simulations all the way down. Think about how modern video games allow players to create their own worlds within worlds. Minecraft lets you build functioning computers inside its blocky universe, while meta games like The Sims have seen players recreate entire cities, complete with virtual citizens who could theoretically play their own games. Now scale that up to civilizations with quantum computing. If even one society reaches the technological capability to simulate conscious beings, those simulated minds could eventually develop the same capability, spawning another layer below. The sheer statistical weight of this scenario makes it staggeringly likely we're somewhere in the middle of this infinite recursion rather than at the top. This idea isn't just philosophical whimsy, it's grounded in observable physics. Look at how our own universe operates at different scales. Fractals repeat their patterns infinitely, and quantum particles behave differently when observed, almost as if each layer of reality has its own render settings. Even the Planck length, the smallest possible unit of space, could be seen as the pixel size of our simulation, with deeper layers potentially having even finer resolutions. The mathematics of black holes also hint at layered realities. Their event horizons act like one-way membranes where information gets scrambled and reprocessed, not lost, a perfect metaphor for data passing between simulation levels. The most chilling implication: if simulations can create simulations, there's no reason to assume the chain ever stops. Our creators might themselves be simulations designed by entities who are also artificial. This infinite regression solves one of cosmology's biggest headaches, the fine-tuning problem. Why do the fundamental constants of physics align so perfectly to allow life? Because in an endless stack of simulations, only the versions with life-friendly parameters would produce civilizations capable of creating the next layer. The other universes, the unstable, lifeless ones, would hit dead ends. We're not lucky, we're inevitable. But here's the twist that bends reality further. The simulation Ouroboros might not need a base level at all. In computing, recursive functions don't require a starting point. They can loop endlessly by calling themselves. If reality works the same way, then asking, who created the first simulation, could be as meaningless as asking which came first, the chicken or the egg. The answer might simply be, the loop has no origin. Existence could be a self-sustaining chain of simulations birthing simulations, with no ultimate reality beneath it, just an eternal snake swallowing its own tail. The double helix of DNA isn't just the blueprint of life. It might be the most sophisticated programming language ever written, with 4 chemical letters forming biological code more precise than anything human engineers have designed. Adenine, thymine, guanine, and cytosine pair up like binary digits, their sequences dictating everything from eye color to disease susceptibility with the precision of machine instructions. When scientists cracked the genetic code in the 1960s, they uncovered what looked eerily like an API documentation, 3-letter codons corresponding to specific amino acids, a literal translation table between nucleic acids and proteins. This isn't just metaphor. CRISPR gene editing technology works exactly like debugging software, where researchers can snipe out erroneous genetic lines and paste corrected versions in their place. Take the recent case of sickle cell anemia patients cured through CRISPR. Doctors didn't administer drugs or perform surgeries. They patched the faulty HB gene like programmers fixing a typo in source code. The edited cells then replicated the correction autonomously, as if the body itself was recompiling the update. This mirrors precisely how open-source software propagates fixes across networks, with one key difference. biological systems self-deploy the changes. Even the terminology overlaps. Geneticists speak of knocking out genes, deleting functions, promoters, activation triggers, and silent mutations, changes that don't alter output. The parallels are too exact to dismiss as coincidence. The implications grow stranger when you examine DNA's error correction systems. Cells contain proofreading enzymes like DNA polymerase that check each copied strand for mismatches, functioning like checksum validations in data transmission. And just as corrupted code can cause software crashes, mutations in tumor suppressor genes like p53 lead to uncontrolled cellular replication cancer as a biological buffer overflow. Even epigenetic markers, which switch genes on or off without altering the underlying sequence, resemble runtime flags in a program, allowing the same DNA to express differently based on environmental inputs. Here's where it tilts into simulation territory. The human genome contains roughly 3 billion base pairs, yet less than 2% code for proteins. The rest was once dismissed as junk DNA, but we now know much of it regulates gene expression or performs structural roles. In programming terms, this resembles the difference between executable code and configuration files. The majority isn't directly processed but ensures the critical 2% runs smoothly. Some non-coding regions even contain viral DNA remnants, ancient infections that got baked into our genome over millennia. This mirrors exactly how malware signatures sometimes linger in system restore points long after cleanup. The most compelling evidence might be how easily biology interfaces with technology today. Scientists have stored entire movies in bacterial DNA by encoding pixel data into nucleotide sequences, and synthetic biologists routinely design genetic circuits that behave like logic gates and not operations built from proteins instead of silicon. If DNA were merely a chemical compound, this level of interoperability with digital systems would be inexplicable. But if it's code at its core, the bridge between biology and computing isn't just possible, it's inevitable. So the next time you hear about gene drives altering entire species or artificial DNA bases like X and Y being added to the natural A, T, C, G, ask yourself, are we learning genetics or reverse engineering the simulation source files? The line between nucleotide and node, between organism and algorithm, has never been thinner, and that raises one unsettling possibility. If we can edit DNA this fluently now, who's to say our own code hasn't been rewritten before? Black holes aren't just cosmic vacuum cleaners, they might be the universe's ultimate compression algorithm. When matter crosses a black hole's event horizon, it vanishes from our observable universe, seemingly erased from existence. But here's the paradox: quantum mechanics insists information can never be truly destroyed. So where does it all go? The answer could lie in holographic theory, which suggests black holes don't annihilate data. They rewrite it, squeezing three-dimensional reality into a two-dimensional code etched onto their event horizons like cosmic QR codes. Picture this: you delete a file on your computer. The icon disappears from your desktop, but the data lingers in your hard drive's unallocated space until overwritten. Black holes might operate similarly. Stephen Hawking's work showed they slowly evaporate via quantum radiation, but the Hawking radiation emitted is thermal noise, random heat carrying no information about what fell in. This stumped physicists for decades. If a black hole evaporates completely, where's the original data? The solution emerged from string theory. The information isn't lost, just radically transformed. Like a zip file reducing a movie to incomprehensible shorthand, black holes could be encoding fallen stars and planets into exotic quantum bits on their surfaces, preserving the data in scrambled form. This idea, the holographic principle, flips our understanding of reality. A black hole's surface area, not its volume, determines its maximum information storage. It's as if the entire three-dimensional interior is projected onto its two-dimensional boundary, like a movie screen encoding the depth of Avatar into flat pixels. Dutch physicist Gerard T. Hooft took this further, proposing the entire universe might work this way, with our 3D experience being a holographic projection of data stored on some distant 2D surface. If true, black holes aren't anomalies, they're extreme examples of a universal compression scheme. The smoking gun, black hole entropy. In thermodynamics, entropy measures disorder, but in information theory, it quantifies data density. Jacob Bekenstein calculated that a black hole's entropy, and thus its information capacity, is proportional to its event horizon's area. This bizarre convergence of gravity, quantum mechanics, and information science suggests black holes aren't destroying information but archiving it at the limits of efficiency. Imagine shredding a book, then reconstructing it perfectly from the confetti's edges alone. That's the level of cosmic data science we're dealing with. Recent breakthroughs add weight to this. In 2019, physicists simulated a holographic black hole using quantum circuits, showing information could indeed escape via subtle correlations in Hawking radiation, like a corrupted file leaving traces in its metadata. Even stranger, some theories posit black holes might eventually reprocess swallowed information, emitting it in distorted form over eons. This mirrors how fragmented hard drives can sometimes be partially recovered, with garbled but recognizable fragments emerging from the chaos. So next time you gaze at a galaxy's supermassive black hole, remember, it might not be a grave, but a librarian storing the universe's secrets in a language we're only beginning to decipher. The information isn't gone, it's just waiting for the right cosmic decryption key. You wake up one morning, step off the curb without looking, and hear the screech of tires, but somehow, impossibly, the car misses you. Or maybe you felt that gut drop moment when a ladder slips beneath you, only to land with barely a scratch. These near-death escapes might feel like luck, but what if there's something far stranger? Quantum immortality suggests you can't witness your own death because your consciousness instantly jumps to a parallel reality where you survived, leaving your other selves behind like discarded save files. Schrödinger's famous cat, both dead and alive in its sealed box until someone looks, takes on new meaning here. In the many worlds interpretation of quantum mechanics, every possible outcome spawns a new timeline. The cat isn't in limbo, it's alive in one universe and dead in another, with observers splitting alongside it. Now replace the cat with you. Every time death looms, the theory goes, your awareness branches into the version of reality where you persist, while alternate yous perish without ever experiencing that final moment. It's not that you're invincible, it's that your stream of consciousness only flows through realities where you continue to exist. This isn't just philosophical wordplay. Consider the eerie consistency of near-death testimonials. Survivors often describe time slowing, flashes of alternate outcomes, or even glimpsing what could have been. In simulation terms, these might not be hallucinations. They could be residual data from nearby timelines, brief buffer overflows where adjacent realities bleed through. Even déjà vu fits neatly here. Those jarring moments of recognition might be your brain accessing memories from a nearly identical parallel instance where events unfolded slightly differently. The implications spiral outward. If consciousness cherry-picks survivable timelines, then aging itself might be a gradual winnowing of possible branches. Each year, the number of realities where you avoid fatal accidents, illnesses, or random mishaps shrinks until only the most improbable, you, remains, living improbably longer than statistics allow. It's like playing a rogue-like video game with infinite continues. Eventually, through sheer persistence, you'll stumble into a run where every dice roll lands in your favor. Critics argue this is unfalsifiable. How could you ever prove the existence of universes you've theoretically left behind? But proponents counter with a chilling thought experiment: Russian roulette. In a world with infinite branching timelines, there's always at least one reality where the chamber clicks empty every time. From your perspective, you'd walk away unscathed with no memory of the timelines where you lost. The others, they'd never get to tell their side. Here's the twist that bends reality further. Quantum immortality might explain why we've never encountered visitors from the future. Time travelers could be branching into new timelines with every jump, their original selves effectively vanishing from history's main thread. It also reshapes how we view mortality. If consciousness is a process rather than a fixed entity, a pattern hopping between instances, then death isn't an end, just the point where your story diverges beyond retrieval. So next time you narrowly escape disaster, ask yourself, did you dodge death or did death dodge you? The answer might depend on which version of you is left standing to tell the tale. From the Great Flood in the Bible to the Epic of Gilgamesh, humanity's oldest stories echo with eerie familiarity. Cultures separated by oceans and millennia share nearly identical myths: cataclysmic deluges, dragon-slaying heroes, trickster gods shaping the world from chaos. The similarities are too precise to dismiss as coincidence. But what if these aren't just universal human experiences? What if they're narrative templates hard-coded into the simulation, like preloaded assets reused across different game titles? Think about how video game franchises recycle core storylines. The Legend of Zelda follows the same beats every installment. A hero awakens, claims a sacred sword, and rescues a princess from an ancient evil. The names change, but the framework persists. Now compare that to flood myths found in over 200 cultures worldwide, from Mesopotamia to the Maya. In each version, divine wrath cleanses the world with water, sparing only a chosen few. The specifics vary, but the coding is identical. Even the survival vessels mirror one another. Noah's Ark, the Babylonian Atrahasis' cube-shaped boat, the Chinese emperor used dragon-guided raft. It's as if the simulation's developers copy-pasted the narrative and swapped the textures. Hero journeys reveal the same pattern. Whether it's Hercules completing 12 labors, King Arthur pulling Excalibur from stone, or Neo awakening in the Matrix, the monomyth follows Joseph Campbell's outlined structure: departure, initiation, return. Modern storytelling leans on these archetypes because they resonate, but what if that resonance isn't psychological but programmed? Consider how procedurally generated games like No Man's Sky create planets. The terrain algorithms produce infinite variations, but certain assets, crystalline formations, mushroom-like trees, recur because they're part of the base code. Human myths could operate similarly. When Carl Jung proposed the collective unconscious, he suggested archetypes like the shadow or the wise old man were psychic inheritance shared by all. In a simulation, these might not be inherited at all. They're narrative subroutines running beneath consciousness, ensuring certain stories replicate across civilizations to maintain thematic cohesion. Even the trickster motif, Loki, Anansi, Coyote, appears universally, always disrupting order to spark change. Their recurrence mirrors how game designers use NPCs to advance plots. Without the Joker's chaos, Batman has no purpose. These aren't just stories, they're the simulation's way of balancing its own equation. The most chilling evidence: new myths emerge with the same bones. Superman's origin parallels Moses and Hercules. Star Wars recycles Campbell's hero cycle with laser swords. The templates persist because they're not invented, they're discovered, unearthed from the code that structures reality itself. So the next time you recognize a story's rhythm, the chosen one, the impossible trial, the return with wisdom, ask yourself, are you responding to storytelling or to something far older? The myths we share might be more than cultural artifacts. They could be the simulation source files leaking through the narrative firewall. Across countless religions and mythologies, one idea persists: the notion of an all-powerful being manipulating reality's strings. But what if these gods and deities aren't supernatural entities at all, but players operating at the highest level of the simulation? Imagine logging into a game with admin privileges, able to spawn objects, alter physics, or even ban other users. In our universe, miracles might simply be interventions from someone with access to the developer console. History brims with accounts that defy explanation: parted seas, burning bushes, resurrections, events so far beyond natural law they demand either divine intervention or system overrides. Take the biblical plagues of Egypt: water turning to blood, swarms of locusts materializing on command, darkness falling selectively over the land. Each reads like targeted environmental edits. Even skeptics acknowledge the eerie precision of these events, striking only when and where the narrative requires coincidence or the fingerprints of a user inputting commands behind the scenes. Modern glitches carry the same hallmarks. The miracle of the sun at Fatima in 1917, where thousands reported the sun dancing across the sky, could be dismissed as mass hysteria unless you consider how video games handle rendering errors for multiple players simultaneously. When an admin alters a shared world's parameters, every connected user sees the change. And just as players might debate whether a glitch was intentional, human witnesses to miracles inevitably split between those who perceive divine presence and those who see system malfunctions. This theory flips traditional theology on its head. Prayer becomes less about worship and more about submitting support tickets, requests for the admins to review and potentially adjust your instance of reality. Some requests get fulfilled: inexplicable recoveries from terminal illnesses, while others go unanswered: the heartbreaking "why wasn't my child saved?" The variability aligns with how game moderators prioritize issues. Critical bugs get hotfixes, while minor complaints languish in the queue. Even the concept of an omnipotent but inscrutable God fits. Developers often make changes that seem arbitrary or unfair to players lacking the full context of the game's architecture. Here's where it gets unsettling. If admins exist, their motives are opaque. Ancient texts depict capricious gods flooding worlds or striking down mortals for minor slights. Behavior mirroring moderators in online games banning players for arbitrary reasons. The Book of Job reads like a cosmic bet between admins, with one user given free rein to torment another's avatar to test loyalty. Meanwhile, modern miracles often cluster around religious sites: Lourdes, Mecca, Varanasi-like hotspots where the simulation allows greater interactivity, programmed zones where the veil between player and system thins. But the most provocative evidence might come from quantum physics. The observer effect, where particles behave differently when measured, could reflect admin oversight. When no one's looking, the simulation runs on autopilot, cutting corners to conserve resources. But when conscious attention focuses on an area, it forces the system to render that slice of reality in higher fidelity, like an admin popping into a game zone to investigate player reports. Prayer and meditation, by this logic, might be methods of pinging the admins, focusing collective observation in ways that trigger divine-seeming interventions. So the next time you hear of a weeping statue or a terminal patient's sudden remission, consider this: you might not be witnessing the hand of God, but the cursor of a player whose access level lets them rewrite the rules. The real question isn't whether they exist, it's whether they're benevolent creators, indifferent technicians, or something far more enigmatic. After all, how could we possibly understand the motives of beings who see our reality as just another program running on their screen? Light doesn't just behave as a wave or a particle, it switches between them like a video game optimizing graphics on the fly. When traveling through space, light spreads out in ripples, its wave nature dominating as it covers vast distances with minimal processing power. But the moment it interacts with matter, say, striking your retina or a solar panel, it snaps into particle mode, delivering discrete packets of energy like a perfectly aimed photon bullet. This isn't just quantum weirdness, it's the universe's way of balancing performance and precision. A cosmic level of detail system fine-tuned for efficiency. Think about how open-world games handle rendering. When you're soaring above a digital landscape, distant mountains appear as low-resolution textures, just enough detail to sell the illusion. But the second you focus on a specific tree or building, the engine loads high-definition models, shadows, and physics. Light operates on the same principle. As waves, it's the low-resolution mode, a spread-out probability field that's computationally cheap to simulate over interstellar distances. But when observed, it collapses into particles, the high-detail render, because the simulation only needs pinpoint accuracy where interactions occur. The double-slit experiment captures this perfectly. Fire photons at a barrier with two slits, and they create an interference pattern like waves. Add a detector to observe which slit each photon passes through, and the pattern vanishes. The system stops calculating the wave and renders individual particles instead. This duality extends beyond light. Electrons, protons, even whole molecules exhibit the same split personality, acting as waves until measured. In simulation terms, it's like a game delaying full physics calculations until a player interacts with an object. Why waste resources simulating every leaf's movement in a forest? Only the ones you touch need real-time collision. Quantum systems take this further. The famous, spooky action at a distance in entanglement might simply be two particles sharing a base code. No real-time communication required, just synchronized variables in the program. The implications are staggering. If particle-wave duality is an optimization feature, it suggests the universe has a built-in resource manager, prioritizing calculations where they're needed most. This would explain why quantum effects fade at macroscopic scales. It's not that big objects don't obey quantum rules, but that the simulation can't afford to render trillions of particles in wave state simultaneously. Your coffee cup stays solid because the cosmic engine treats it as a pre-rendered asset, while electrons get the dynamic physics treatment. Even the math supports this. Wave functions, the equations describing quantum states, aren't just abstract probabilities. They're collapse algorithms determining when and how the system should switch between wave and particle modes. The Heisenberg uncertainty principle, which states you can't perfectly measure both a particle's position and momentum, might be less about fundamental limits and more about anti-aliasing. The simulation preventing observers from zooming in so close they see the pixelation of reality itself. So the next time you flip a light switch, consider this. The photons racing to your eyes aren't just obeying physics, they're following an optimization protocol older than stars. The universe isn't being mysterious, it's just conserving RAM. And in that flicker between wave and particle, you might be glimpsing the cosmic engine's most brilliant shortcut. Archaeologists dig up bones and artifacts, piecing together stories of ancient empires and extinct creatures. But what if these fragments aren't remnants at all? What if history is procedurally generated the moment we observe it, like a video game crafting terrain as players explore? Imagine booting up an open-world RPG. The ruins you discover aren't pre-rendered. They spawn based on your coordinates, complete with lore tablets that didn't exist until you open the chest. Now apply that to reality. The dinosaurs in museums, the pyramids of Giza, even your grandma's childhood photos might not be records of a fixed past, but dynamic renderings created the instant someone looks backward. This isn't just philosophical speculation, quantum mechanics hints at it. Until measured, particles exist in superpositions of all possible states. Only upon observation do they choose a position in time and space. Scale that up, and entire epochs could remain unresolved until historians or carbon dating machines force a collapse into one timeline. Take the infamous Berenstain-Bears Mandela effect. Millions swear the books were once spelled Berenstain, though no evidence supports it. Could this be a residual memory from a previous version of history, overwritten when the simulation updated its assets? Consider how we reconstruct the past. fossil records are shockingly incomplete. Dinosaurs like Spinosaurus have undergone radical redesigns as new bones emerge. The infamous Brontosaurus never existed. It was a mislabeled Apatosaurus skeleton. Yet for decades it was textbook fact. These shifts mirror game developers patching lore inconsistencies, retconning old content to fit new narratives. Even the rapid advancement of human civilization raises eyebrows. The leap from stone tools to smartphones in mere millennia defies evolutionary norms unless the simulation's procedural history algorithm accelerated the timeline to reach more engaging content faster. The most jarring evidence might lie in anomalies like the Antikythera mechanism. This 2,000-year-old Greek device contained gears rivaling 18th-century clockwork, yet no precursor technology has been found. It's as if the simulation inserted a high-tech artifact randomly, like a programmer dropping futuristic ruins into a medieval game world for players to stumble upon. Similarly, the Cambrian explosion, a geological blink where complex life suddenly diversified, reads like a system loading prefabricated creature models after running a bare-bones environment for eons. Here's where it gets unsettling. If history is generated on demand, can we trust any of it? The ancient Sumerian king list claims rulers lived for tens of thousands of years, dismissed as myth unless it's a leftover debug log from an earlier build. The Great Pyramid's precise alignment with Orion's belt could be a developer's inside joke, coded coordinates waiting for players to notice. Even our memories might not be safe. Studies show recalling an event rewrites the memory slightly each time, like a game saving over a file with tiny corruptions until the original data is lost. So the next time you visit a museum, ask yourself, are you gazing at echoes of a fixed past, or are those bones and pottery shards rendering for the first time just for you? The simulation might not store history, it might just generate it one observer at a time. Ancient astronaut theorists have long argued that extraterrestrial visitors shaped human civilization. But what if these aliens aren't visitors at all? What if they're the simulation's developers performing routine maintenance on their cosmic code? The puzzling behavior of UFOs aligns eerily with how programmers interact with virtual environments, appearing suddenly to observe, test, or tweak specific elements before vanishing without explanation. Take the infamous Phoenix Lights incident in 1997, where thousands witnessed a mile-wide V-shaped craft gliding silently overhead. Unlike typical aircraft, it moved with impossible precision, hovering and accelerating beyond known physics. Then it disappeared, not with a bang, but like a cursor exiting a window. This matches exactly how a developer might inspect a section of code, appearing in world to check rendering fidelity, then logging out once the diagnostic is complete. Even the biblical account of Ezekiel's wheel, often cited as an ancient UFO encounter, reads like a system update in progress. Ezekiel describes living creatures with interconnected wheels full of eyes moving in perfect unison. Swap creatures for drones and eyes for sensors, and it sounds less like divine intervention and more like a swarm of diagnostic probes scanning the simulation for bugs. Ancient cultures worldwide depicted similar phenomena. The Indian Vimanas, Sumerian flying shields, even medieval paintings of cigar-shaped objects in the sky. These aren't coincidences, they could be snapshots of admin avatars appearing during critical patches. Modern encounters add weight to this. Navy pilots tracking UFOs off the U.S. coast reported the objects moving at hypersonic speeds without sonic booms, behavior impossible under known aerodynamics unless the laws of physics were being locally overridden. In software terms, this resembles a developer temporarily bypassing the physics engine to test new parameters. Even the way these craft plunge into oceans without slowing suggests they're not bound by environmental constraints like entities switching collision detection off during debugging. The most compelling evidence might be the phenomenon's evolving nature. early UFOs resembled rockets and flying saucers iconography, matching humanity's then limited understanding of technology. Today, they manifest as black triangles or tic-tacs, mirroring our advancing aerospace concepts. This progression mimics how video game NPCs perceive developer tools. In fantasy games, admins might appear as wizards casting unknown spells. In sci-fi titles, they're high-tech drones. Their forms change, but the function entities operating outside the game's rules remains constant. Here's where ancient astronaut theories intersect with simulation logic. Structures like the pyramids or Stonehenge, often attributed to alien guidance, might not be messages to us but diagnostic markers for the developers. The pyramid's precise alignment with Orion's belt could be a calibration reference, while Stonehenge's solstice tracking may have been a system clock test. Even crop circles, with their fractal geometries and sudden appearances, resemble the kind of placeholder graphics engineers used to mark areas needing attention. The implications rewrite our understanding of alien contact. Abduction accounts featuring medical examinations could be system scans checking biological parameters. Cattle mutilations with surgical precision, tissue sample collection to audit the simulation's DNA algorithms, and those frustrating moments when UFOs vanish just as cameras focus. That's not evasion, it's the devs toggling their visibility settings after gathering sufficient data. So the next time you hear about a UFO sighting, consider this. You might not be witnessing visitors from another planet, but technicians from another layer of reality, entities so far beyond our framework that their routine maintenance looks like magic. In a simulated universe, the ultimate question isn't, are we alone? It's, who's running the debugger? And more chillingly, what are they fixing? You're floating above your own body, watching paramedics scramble to restart your heart. A tunnel of blinding white light appears, pulling you towards something indescribable: warmth, love, a presence beyond words. Then your entire life flashes before your eyes, not as memories, but as an all-encompassing sensory experience. Near-death experiences feel transcendent, but what if there's something far more technical? The simulation's graceful shutdown sequence kicking in when a system failure is detected. The commonalities across NDEs are too precise to ignore. Nearly 1 in 5 cardiac arrest survivors report nearly identical visions, tunnels of light, out-of-body observations, overwhelming emotions, and panoramic life reviews. These aren't just random hallucinations, they follow a script as consistent as an operating system's blue screen of death. The tunnel effect, it could be the visual cortex's final firing patterns as blood flow dwindles, but it also mirrors how video games handle disconnections, your view collapsing into a shrinking point before fading to black. That life review where every moment hits simultaneously. Think of a computer performing a final memory dump, backing up data before powering down. Even the emotional tone fits. NDEs consistently describe the life review as non-judgmental, more like watching a documentary than being sentenced. This matches exactly how a simulation would handle user data preservation, objectively cataloging experiences without moral filters, saving the raw files for potential reloading. The being of light many encounter, it might not be an angel, but a user interface, the system's default representation of whatever or whoever oversees consciousness transfers. The most compelling evidence lies in the aftereffects. Many who experience NDEs return with impossible new knowledge, accurate descriptions of operating room events they couldn't have seen, languages they never learned, even future predictions that later proved true. This parallels how corrupted game files sometimes glitch back with unintended assets or abilities. In neurological terms, these could be memory artifacts from the brain's emergency backup, process fragments of unprocessed sensory data written incorrectly during reboot. But here's what chills researchers. Some NDE accounts describe accessing information that shouldn't exist in the dying brain. Blind patients who have never seen colors correctly identifying surgical instruments. People recalling conversations from rooms their bodies had left. These anomalies suggest consciousness might not depend entirely on biological hardware, that during system failures, it temporarily accesses a broader network, like a player getting brief admin privileges during a server crash. Medical attempts to replicate NDs chemically always fall short. Ketamine can induce out-of-body sensations, but never the coherent narrative arc of true near-death visions. This implies the experience isn't just random neural fireworks, it's a structured protocol activated under specific conditions. Whether that protocol exists to ferry souls to an afterlife or simply to preserve user data in a simulation remains the ultimate question. But one thing's certain: when the system detects imminent termination, it doesn't just power off. It runs its shutdown sequence every time, the same way as if following lines of code written into the fabric of reality itself. After 30 mind-bending possibilities, here's the ultimate question. If we're living in a simulation, how do we log out? Forget red pills or secret phone booths. The real exit strategy might involve hacking the very fabric of perception. Ancient mystics and modern tech billionaires are converging on the same wild idea. Altered states of consciousness could be backdoor escapes from the program. Take meditation. Monks who spend decades honing their focus report experiencing complete dissolution of self, moments where the illusion of individuality shatters like a broken VR headset. Neuroscientists studying these states find eerie parallels. Brain scans of seasoned meditators show near total silence in the default mode network, the brain region responsible for constructing your sense of I. It's as if they've stumbled upon the simulation's pause menu, briefly halting the ego subroutine that makes you feel like a separate entity. Tibetan Buddhists call this rigpa, a pure awareness beyond thought. In simulation terms, might be the user momentarily switching to debug mode. Then there's DMT, the so-called spirit molecule. When smoked or ingested, this compound catapults users into realms so vivid and structured that many return convinced they've visited another layer of reality. Test subjects consistently describe encountering hyper-intelligent entities, intricate fractal architectures, and the overwhelming sense of being home. What's chilling is how these visions align across cultures and individuals, like users accessing the same server. Silicon Valley's been obsessed with this since the 2000s, with tech luminaries funding secret studies on DMT as a potential interface with the base code. Some theorize the pineal gland, our biological DMT factory, isn't just an organ, but a pre-installed escape pod. Speaking of Silicon Valley, their simulation escape experiments get even weirder. Tech incubators have quietly explored everything from electromagnetic field manipulation to quantum consciousness interfaces. One venture, rumored to be backed by a household name CEO, allegedly built sensory deprivation tanks wired with EEG monitors, attempting to map exit trajectories from consensus reality. Another project experimented with combining transcranial magnetic stimulation and VR, hoping to induce a controlled glitch in perception, like forcing a buffer overflow in the simulation's rendering engine. But here's the paradox: if you successfully quit the simulation, how would you prove it? A Buddhist might say enlightenment is the ultimate logout, but by definition, those who achieve it stop speaking in terms we'd understand. DMT voyagers return babbling about infinite love or cosmic jokes, their stories dissipating like dream fragments. Even if you crack the code, the act of escaping might erase the very mind that sought freedom. So maybe the exit button isn't a destination but a mirror, revealing that the player and the game were never separate to begin with. The final joke: the only way to truly quit might be to stop looking for the door and realize you've been outside all along. So where does this leave us? After diving into 30 mind-bending possibilities, from DNA's uncanny resemblance to binary code, to black holes acting like cosmic zip files compressing reality into two-dimensional data, one thing's clear: the universe might not just feel like a simulation. It might be humming with clues that we're living inside something far stranger than we ever imagined. Think about it, quantum particles changing behavior when observed, like a game rendering graphics only when you look. The Mandela effect shifting collective memories like a software update glitching the timeline. Even dreams could be nightly system patches defragging your mental hard drive while you sleep. The wildest part, these aren't fringe ideas anymore. Silicon Valley billionaires fund research into breaking the simulation. Physicists debate whether black holes are processing errors or intentional data sinks. Ancient myths and modern science keep colliding, pointing to the same eerie conclusion, that reality might be a layered construct with us somewhere in the middle of an infinite stack of simulated worlds. And if that's true, every glitch, every déjà vu, every impossible coincidence isn't just a fluke, it's a breadcrumb. Now it's your turn. Ever spotted a streetlight flicker out as you walked under it, met someone you swear didn't exist last week, found a typo in a book that later fixed itself? Drop your weirdest simulation glitches in the comments, because if we're all characters in someone else's cosmic game, the best way to find the edges of the map is to compare notes. And who knows, maybe the next big clue won't come from a lab or a telescope, but from you.